Right, good morning everybody. Good afternoon. Sorry, good afternoon. Welcome back. I feel I'm seeing so much of you lately. This is the third lecture of Team 7, so we're almost done with this component, which means you'll almost be done with general and physical chemistry, and then you'll start with organic chemistry next week, Wednesday. Two very important announcements. The first is, again, the semester test. I've already mentioned that. I'm going to mention it every day that I see you. That's Teams 5 to 9. But as always, stoichiometry forms a central part of everything. I'm not going to ask stoichiometry questions explicitly, but you better be good with stoichiometry because it fills in with all of these themes in any way. Then next week, Wednesday, is a Monday timetable. So that means practicals for the Monday group will happen next week on Wednesday. That'll be practical 5. And then the Thursday group will have practical 5 the day thereafter on Thursday. So just keep note of that. And then a reminder to start studying for Theme 8. We should be able to finish with acids and bases tomorrow. Maybe we'll have a little bit left for next week, Tuesday. Then the rest of that lecture I will spend on giving you an outline and some tips and pointers for Theme 8 and give you some advice on what to follow and maybe do an example or two. I do believe that's that. Right, so going back to acids and bases, we're going to amp up the complexity even more today. So we've looked at pH and pH, pOH, the nature of acids and bases. Now we're going to start putting this together and see what happens when acids and bases react. The point of this is to understand titrations, which you've already covered a little bit in your practicals, and then finally to get to buffers. So a lot of biological reactions do involve acids and bases. It's a really active part of biology. But more important for that is the pH of a biological solution, which has to be kept very, very, very closely constant. So, but to get to all of that, we first need to understand acid-base reactions. So generally everything in acids and bases can be split up into whether we're reacting with a strong acid or a strong base or a weak acid and a weak base, and really all that entails are the equilibria. So for a strong acid and strong base, equilibrium lies all the way to the right, and for a weak acid or base, it lies all the way to the left. So if you can remember that, if you can understand that, then most acid-base equations do become very easier. So for instance, if we react a strong acid with a strong base, so for instance, hydrochloric acid with sodium hydroxide, each one of these will ionize, and it will ionize completely, which means HCl becomes chloride and the proton immediately grabs the water to become hydronium. So that means when we react these two, we can really just write out the ions involved. So we can write out the complete ionic equation. So that'll be our hydronium and the chloride from HCl interacting with the sodium and hydroxide from the sodium hydroxide. The hydroxide and the hydronium will combine because this is a strong acid, this is a strong base. So they will react and neutralize to become water, and then we are left with our counter ions, the chloride and the sodium cation. Now that means from this complete ionic reaction we can just write out the net ionic equation. So really the only two things that are reacting are the hydronium and the hydroxide to give water. The rest, in other words, the chloride and sodium are spectator ions. So writing out the net ionic equation makes it easy to see what is actually happening without all of the counter ions in the solution. So if we have a strong acid with a strong base, really all that's happening is we've got hydronium that is being neutralized by hydroxide to just give water, which anyway forms part of the solvent, so we won't account for that within equilibrium. Right, so that means if we have an equal mole amount of HCl with an equal mole amount of sodium hydroxide, that means 1 mole of hydronium is going to react with 1 mole of hydroxide, so they will neutralize completely, which means we won't have any excess or acid or base left in the solution, and we expect a solution with a pH of 7. So whenever we mix strong acid and strong base together, and we've got the exact same mole amount, we get a neutral solution. That's also, if you remember from your titration practical afterwards, when you were busy with the cleanup, you had to neutralize your acid and base waste. So that was literally taking all of your acid, adding enough base until you get a completely neutral solution. If we then mix a weak acid with a strong base, the strong base is still going to ionize completely, which means the net ionic component of this will only be the hydroxide ions. On the other hand, a weak acid like formic acid, the equilibrium will lie very much to the left, so it doesn't ionize. So the active species in a solution will be the acid itself, rather than it's a conjugate base or the conjugate acid, which is hydronium. So in this case, when we have a weak acid with a strong base, we really have our weak acid itself reacting with the hydroxide from the strong base. Now, this is still an acid, this is still a base, so that means acid will donate its proton, base will accept the proton. So the hydroxide becomes water, and our acid becomes its conjugate base when it gives up a proton. So that'll be our net ionic equation. Obviously, the complete ionic equation will have the sodium counterion as well. Now, when we look at this, we can then go back to what we did, I believe it was on Friday, we looked at equilibrium of weak acids. So, looking at all of these species, we've got an acid and a base, a conjugate acid and a conjugate base. The conjugate acid is the conjugate acid of a strong base. So this should be a weak acid, and the conjugate base is the conjugate base of a weak acid. So this should be a relatively strong base as well. However, hydroxide is one of the strongest bases that we know. So that means this should be a stronger acid than the conjugate acid, and the hydroxide should be a stronger base than the conjugate base, which means in this case, equilibrium will still lie to the right, as we did on Friday as well. And that means, however, if we were to mix equal mole amounts of formic acid and sodium hydroxide, so that we have the same concentration of the acid as well as the hydroxide base, these two will neutralize just based on stoichiometry. So 1 mole reacts with 1 mole. So we reduce the hydroxide, we reduce the acid, the equilibrium lies to the right anyway, but we are left with this relatively strong conjugate base, which hasn't been neutralized. So that means if we mix equal mole amounts, the hydroxide and the acid will neutralize, or will cancel, but we will be left with a slightly basic solution because we are left with the conjugate base. That didn't happen if we had a strong acid. The pH of this will be more than 7, but it will be dependent on the ionization constant of this conjugate base. So if this conjugate base is very strong, we'll have a very high pH. If the conjugate base is relatively weak, we'll have a pH closer to 7. The same then happens if we have a strong acid with a weak base. So again, for instance, hydrochloric acid with ammonia. The hydrochloric acid ionizes, gives us hydronium. The ammonia, the equilibrium lies to the left, so we are left with mostly ammonia in solution. So that remains as a reacting ion or a reacting species. This accepts a proton from the hydronium to become ammonium ion and water. So we can do the same type of analysis. We've got an acid and a base, a conjugate acid and a conjugate base. Our acid on the left is stronger than the conjugate acid, and our base on the left is stronger than water, our conjugate base. So again, for this, equilibrium will lie to the right. We'll have equal mole amounts of this will neutralize based on stoichiometry, but we are end with this conjugate acid in solution, which will lower the pH. And this will be dependent on the pKa of this conjugate acid. So the same story, just the opposite around. And if we were to mix a weak acid and a weak base, none of these will ionize completely. So we are left really with formic acid in this case reacting with ammonia. This is what will be our net ionic equation. Formic acid donates a proton to ammonia, which becomes ammonium and bicarbonate ion. Now in this case, we do still have acid-base, conjugate base, but we can't necessarily say which one will be stronger than the other. We can do it for this specific example, but in general, we won't be able to say that. We'll need to look at the pKa and pKb of these conjugate acids and conjugate bases. So if we have a weak acid and a weak base, we might get an acidic solution, we might get a basic solution. It really just depends on the strength or the relative strength of the acids and bases in our solution. Right. Now, given this, there's a short little summary that I gave you as well, just to put it all together. This is everything I've just said already. The 4 types of acid-base reactions we can have, and all of this is just relative to whether you have a strong base or a strong acid. which means does it ionize completely and give us hydronium and hydroxide, or does it ionize incompletely and give us the actual acid and the actual base? And then again, if we have any strong acid and any weak base, it is always going to be an acidic solution or a basic solution if it's the other way around. And only for weak acids and bases do we need to really look at the specific pKa's and pKb's. Now, with this information, we can now move on to titrations and then finally buffers. So titrations I'm not going to cover in detail because we actually moved some of the theoretical component of this course to the practical side. So our thinking was that you anyway had to study and prepare for the practical. You did the practical quite in depth as well, and that really gives you the knowledge you need for titration. So I'm not going to spend too much time on this. If you need more information, you can go back to your textbook as well and then revisit your practical notes to see that you fully understand it. The basic idea, however, of a titration is an acid-base reaction that we isolate one of the unknowns. So usually it's to determine concentration, but we can use titrations to determine, for instance, the pKa or pKb of an acid or base as well, and specifically at a different temperature than we might have reported values for. So whenever we have some unknown quantity, whether it's concentration or a physical constant like pKa, we can do a titration by controlling all of the other variables. So in this case, we have a known concentration and volume of an acid or a base. Then we're going to add something to that, a different one, an acid or a base, and we'll effectively know the exact volume that we add until another observable changes like the pH. So typically we have an acid or a base with known concentration and volume. Then we titrate that acid or base with another acid or base, but we have the volume that is known, but we don't know the concentration. We keep on titrating that until we see a color change if we're using a color-based indicator, or more often than not, we'll just use a pH meter. And then we can measure when the pH suddenly jumps and spikes and makes a drastic change. I just want to actually go ask someone, it's like, what happened? What? Like, is it one of our students that he walked in here and it's like, I'm not into chemistry today. Anyway, so titrations usually make a very sudden spike in pH. That's why we can use a color-based indicator, even though the color might not be 100% where our equivalence point might be. But the moment we get to the neutralization point, when we've got equal amounts of acid and base, suddenly the pH makes a very drastic change, and that's because the pH is a log scale. So initially we don't see a large change in pH as we start titrating, because a small difference won't make a difference to pH of 2, because it's a log-based difference. But as we get closer to pH 7, suddenly a small difference in the amount of acid or base makes a large jump in the pH. So that's why we can actually get really close to accurate results using color-based indicators, even if that color-based indicator doesn't actually change at pH 7, but maybe at pH 9. Either way, when the color has changed, or when our pH have made a dramatic jump, we say that's our end point. It's marked by a significant shift in the equilibrium of this acid-base reaction. And and that will tell us we're at the end point. So then we can just jot down the volume. And based on our volume and our known volume concentration, we can figure out our missing variable, whether it's concentration or pKa or anything of that nature. So again, we'll just differentiate a little bit between a strong acid and a strong base, weak acids and weak bases. Then if we do a titration with the strong acid and strong base, we're really just doing a reaction. So this is just an acid-base reaction. That's why I'm not even doing examples of acid-base reactions, because these are just really titrations. So if we have a strong acid and strong base, this will be our net ionic reaction. The hydronium is the amount that we've added by a strong acid. The hydroxide is the amount we've added by a strong base. If the amount of the strong acid is more than the amount of the strong base, we'll be left with a acidic solution. If the other way around, we'll have a basic solution. And if we add just the correct and equal amounts, we get a neutral solution. And that's then obviously the goal of a titration, is to get this exactly the same amount. And once we get to that point, we say we've reached the equivalence point. So the equivalence point, we've got the equal mole amounts of acid and base. This is defined by stoichiometry. So if we've got a diprotic acid or base, for instance, this will be a different equation that we have here. There might be 1 hydronium and 2 hydroxide. And this is a theoretical point, so we can never really truly reach the actual equivalence point because this is the exact to the 10th significant figure of the amount of acid and base that we've added. If we've got a strong acid and strong base, remember, this completely neutralizes, so we've got pH 7. The more practical point that we note is the end point. So that's when we stop the titration, that's when we see a color change or anything like that. And generally speaking, we want to design our experiment and practice our skills until the endpoint and equivalence point is as close together as possible. So in your practical, you did, I think, 4 titrations with the idea that you can get an average. So each time we redo it, we get a slightly different endpoint, but by taking the average, we should be aiming to be close to that equivalence point. And then that gives you a bit of practice as well, so that you realize how easy it is to overshoot the color. And then hopefully many of you just got the perfect color at least once, which means your endpoint was very close to the equivalence point. Yes, sir.
So is your endpoint more like a range? Because there's a range between which you can get that kind of change.
Yes, so the endpoint isn't, the equivalence point is theoretical. So there is a theoretical exact equivalence point, which means if we add 1 mole of hydronium, the equivalence point will be when we add 1 mole of hydroxide. However, in practice, I mean, we do measurements. So that means you use a burette, which only has maybe 2 significant figures. So you won't get the exact same mole amount, which means our endpoint is the best possible point that we can notice the change in pH, whether using a color indicator or a pH meter, that we can say the reaction has been neutralized in this case. Right, so let's quickly do this example. This is just to illustrate a bit really what happens during acid-base titration. So in this case, we actually have all of the known quantities. So that's why I say this is to illustrate what is happening. We are taking 50 mol of a 0.1 molar hydrochloric acid solution. We titrate that with a 0.1 molar sodium hydroxide solution. And then we just see what will happen to the pH once we've added different amounts of the sodium hydroxide. But in this case, all of our variables are known. We know both of these are strong acids and bases, so we don't need to take pKa or pKb into account. So we'll just calculate the pH at these different points during the titration. So initially, we'll have 0 mol of the sodium hydroxide. So that means we'll only have 50 mol of a 0.1 molar hydrochloric acid solution. It's useful to just write out for us the reaction that we actually expect. So that'll be hydronium plus hydroxide to give us water. Right, now if we don't have any hydroxide, that means this will be 0. So all of our hydronium concentration or ions will come from the acid. Technically, we have 1 times 10 to the power minus 7 molar of hydronium already present in water, but we are dealing with 0.1 molar hydrochloric acid solution. So that is about 1,000,000 times more than what we have in solution, so we don't need to take into account what we start with. So that means if we want to calculate the pH, pH is minus log of the hydronium concentration. And we do have the hydronium concentration because HCl is a strong acid. So every mole of HCl will fully ionize to give us hydronium, which means this will just be equal to minus log of 0.100 molar. And remember, this is concentration that we take, so we don't even need to take into account the volume of HCl at this stage, which I believe 0.1 pH log. Let's just do it on a calculator. Yes, I was right. So we'll have a pH of exactly 1 if we have a 0.1 molar hydrochloric acid solution. Now, we will start adding hydroxide. So we know the concentrations are exactly the same. So now we have 50 ml and we're going to add 25 ml of sodium hydroxide. So exactly half of the total amount of hydrochloric acid. So for all of this, there's really two ways we can do this. As we add our sodium hydroxide, we are diluting our hydronium content. And the sodium hydroxide itself, which starts at 0.1, will be diluted as well. Because this is 25 ml at the moment. But we add that to 50 ml, so the new volume will be 75 ml. So both of our components get diluted. So either we calculate the mole amounts, and first calculate how many moles will cancel off with each other, and then we calculate the final solution, or we can dilute the hydronium first, dilute the hydroxide first, and then compare the concentrations directly. Let me do that the second way, which I consider the longer way around first. So that means our initial hydronium concentration will be 0.05 liters times 0.100 mole per liter. That is our mole amount, and then we dilute that to 0.075 liters, which is our new concentration. So this is just C1, C1V1, C2, V2. I just do this with units. I find that easier because now I can see my units will cancel off. Liters with liters, and we end up with mole per liter. Right, so that is 0.05 times 0.1 divided by 0.075. So our initial hydronium concentration is 0.06666, etc. molar. Then we can look at what is our initial hydroxide concentration that we've added. This is 0.025 liters times 0.100 mole per liter at our new volume of 1 over 0.075 liters. So that'll be exactly half of what we're dealing with now, so I'm not going to do the entire one. That'll be 0.03333, etc. And now, based on this reaction that we have, that means we've got the same, we've dealt now with concentration, which is mole per liter. We've got the same volume. So that means we can just subtract these concentrations from each other, which means our H3O plus concentration at our new equilibrium will be the initial, which is 0.0666, etc., minus our hydroxide concentration, which is 0.0333, etc. And you should have been able to see this ahead of time. That means we end up with 0.0333 molar of hydroxide concentration. So exactly half after the dilution and half of the cancellation, which means our pH at this state is minus log of hydronium, which therefore will be oh, that's a bummer. Somewhere in that range, minus 1.477, etc. Our significant figures are 3 significant figures in all cases. So for a logarithm, that means we'll write it to 3 decimals. So we can see our pH, which went from 1 when we only had hydroxide. Now we effectively neutralized half of our hydroxide by adding half of the same volume. But our pH only made a marginal increase from 1 to 1.5, more or less. Then for the third part of this, and I'm going to do this the other way and a little bit quicker, we are now adding 49.5 ml of the sodium hydroxide solution. So almost exactly the same amount that we have HCl. So that means our hydronium concentration at this stage will be our mole amount differences. So the mole amount of hydronium minus the mole amount of hydroxide, which is what we've added. So that means the two will have reacted with each other, divided by our new volume, which is going to be 50 mol plus 49.5 mol. So that is going to be 99.5 milliliters. So 0.0995 liters. So the mole amount this will be our concentration, 0.1 mole per liter times 0.05 liters minus our mole amount of the hydroxide, 0.1 mole per liter, and we've added 49.5, 0.0495 liters, divided by volume. So that gives us, for the actual difference in our mole amounts, that'll be 0.1 times 0.05 minus 0.1 times 0.0495. So this is the amount, mole amount of hydronium ions that we have left, and we'll just divide it by our new volume to get our concentration of 0.000502, etc. molar. And then we just take the log amount of this. So now our pH is 3.298. Which, with three significant figures, will be 3.298. Excellent. So we can see how suddenly, when we only had half the amount of hydroxide relative to hydronium, our pH was only 1.47. Now, when we have equal amounts, our pH jumped to 3.29. So we had a very drastic increase in the pH, and that happens even more as we get closer and closer to the equivalence point. Yes, sir?
Is it possible to have a pH that goes beyond the range of 0 to 14?
Yes, absolutely. So do yourself a favor and go calculate the pH of, make it a 10 molar HCl concentration. Go do that for the log. Okay, so the last part of this I'm not going to do. At 50.5 mol of the sodium hydroxide, you can just work it out. At this point, we'll have to reverse our calculation. So either calculate OH and then calculate the POH and from there the pH. But let me just show you what happens to the pH. So when we add 25 mol of sodium hydroxide, we only made a 0.5 difference to the pH. Then we add almost another 25 mol, but 24.5 mol, which jumped the pH from 1.5 to 3.3. And now we add a single milliliter extra of sodium hydroxide between 49.5 and 50.5, and our pH jumped from 3.3 to 10.7. So that's what I mean with we make a very drastic pH jump the closer we get to the equivalence point. And that's why when you did the titrations, you kept on swirling, it remained blue, whatever color you used, and then literally suddenly you add one drop to many, and it becomes this horrible yellow color where you were thinking like, this is going to be the drop that makes it exactly green. So if you didn't get that 100% equivalence point in the practical, that's actually not bad skill on your side. It is actually the fact that one drop might literally be enough to put it over from a 3.3 pH to a 10.7 pH. So I mean, if your drops were milliliter sizes and you had this type of setup, you would suddenly see that massive jump in pH. So those of you who got exact equivalence points, I think it was a green color, that means you were actually lucky. And I had just sort of felt directly on that point between the two. So if you want to do this more accurately, we actually use very dilute solutions so that the changes are less drastic at a time but then it does take much longer and we need much larger glassware. Right. I do believe we've got another exercise. I'm not going to do this exercise. Please do this. This is an actual titration exercise. So we take 50 ml of a known, you know what, I'll just do this quickly. There's also two ways of doing this. So if you read this, we have a known concentration of HCl, and we titrate it with sodium hydroxide. So strong acid, strong base. That means we can immediately write out our equation. We know how much HCl we start with, which means we can convert this to a mole amount. We say the end point was reached when we added 197 milliliters of sodium hydroxide. So that means this, we can assume, will be the same mole amount as the HCl. So that means at the end point, our mole amount of HCl will be approximately equal to the mole amount of sodium hydroxide. Then we can turn this into concentrations by dividing by the total volume. And from there, we can calculate the original sodium hydroxide concentration. There's a bit of a shortcut that your textbook actually also uses, and that is using units and dimensional analysis. So if we want to calculate NaOH, we can say that'll be our concentration of HCl and then we'll convert, or we'll take a ratio of the volume. So for every, or it took us 197.0 milliliters of sodium hydroxide to neutralize 50.0 milliliters of HCl. So effectively, instead of converting each one separately, we are just doing this conversion in line. So if we do the dimensional analysis of this, we see this is the ratio at the same volume, because after we've added all of this, we've got the same volume, 197 plus 50 mol. So this is our ratio, which effectively is going to be a mole ratio if we've got the same volume solution. And in this case, milliliters will cancel off, HCl will cancel off, and we end up with mole sodium hydroxide per liter. So if we calculate that, we see that is Y. That is going to be a 0.1 times 197 divided by 50 is equal to 0.394. Now I do not get the same answer. Right, so I don't like this shortcut, honestly. So I think I'm missing something. So do it at home using proper stoichiometry. Don't look at your textbook, it's silly. And work out what is the mole amount of HCl, the mole amount of sodium hydroxide, and from there on you can really easily calculate the concentration of the original sodium hydroxide solution. Right, I'll continue. Right, the last part of titrations is also easy. I'm not going to do these examples. You did do the example in the practical, so do work through the examples itself, but I want to get as quickly as possible to buffers so that we have a bit more time there. We can also titrate a weak acid with a strong base, or a strong acid with a weak base, and that's why I did the reactions with you beforehand, because all of this remains the same. We've got an acid and we've got a base. This is what we're titrating against each other. And it's also just stoichiometry. So our endpoint equivalence point will be when our mole amount of acid is equal to the mole amount of base, or the concentrations are equal to each other because we're dealing with the same volume. So that'll be our equivalence point. However, unlike a strong acid and strong base titration, our equilibrium contains this conjugate base, which means this will increase the pH because it's present in the equilibrium. So for a weak acid with a strong base, our equivalence point will happen at a pH above 7. This will depend on how strong this conjugate base is. If it's a very weak conjugate base, this will be close to pH 7. We can use the same indicators that you used in your practical. If this is quite a strong conjugate base, then the pH will be significantly above 7, which means if we use an indicator that changes at pH 7, but the equivalence point is actually at pH 11, that means we'll get an incorrect endpoint or incorrect equivalence point. So we need to at least do this experiment a few times to understand really where the titration occurs or where the endpoint occurs, and from there on we can use the correct indicator at the correct pH range. So as I said, this is basics, so the pH will be above 7, and this is what the pH curve will look like if we start with a strong acid and we titrate it with a weak acid and we titrate it with a strong base. Initially we'll have quite a slow increase in the pH until we reach our equivalence point, which you can see here is above pH 7. So at that point our pH almost changes instantaneously, and we then slow down the pH growth after that as well. But we can see this is not at 7 but rather above 7 because of the presence of this conjugate base. A strong acid with a weak base is the same thing. So again, we've got our weak base as part of the net ionic equation. Our equivalence point now it will be slightly acidic because we've got this conjugate acid in the presence of the solution. So if we start with a strong, if we start with our weak base, we titrate that with a strong acid. Means we'll initially have a high pH. pH will slowly decrease until we get close to our equivalence point, which will now be less than 7, and we see a sudden and drastic pH change. And then again, I give you some exercises for you to do. Please do these. There'll be more in your owls as well. Titration is easy, but surprisingly difficult to confuse yourself with. So it's one of those things, if I do it, you just watch what I'm doing and think, oh, this is fine, I understand this, it's easy. And then you sit with it yourself and you realize, oh, something's wrong. Exactly what happened to me a slide or two ago with the shortcut that the textbook gives, and now I'm not confident enough to do it on my own. I'm joking. This is really not difficult work, but don't confuse yourself when you do it. So work through these exercises, please. I don't think there'll be a tutorial on this because I think your next tutorial will be on organic chemistry. So that means you'll be mostly on your own for these questions. Right. Then the last part of theme 7 is on buffers. Now, I will do a lot of exercises for buffers tomorrow. Yes, sir?
Sorry, if we don't know what the acid is, let's say it's someone's called an acid, we don't know what the acid is or the concentration, we have to use the universal indicator.
So he asked a very good question, and surprisingly this will come up at some point in your career possibly, as what if you don't know whether you're dealing with a weak acid or a strong acid, or you don't even know if it's a weak acid, how weak it is, how strong it is, so you don't have an idea of where the equivalence point will be. So we do have universal indicators. Generally speaking, the way we would do this is you can buy a very cheap pH meter on Takealot, which will do the job just fine. And then you start doing this titration. So you start with a known, if you've got some base, you don't know what type of base it is, you start with a known strong acid. You start adding it and you record the pH and plot that. And then eventually you'll see this quick jump in the pH, which will tell you, oh, the equivalence point will be somewhere in this straight line area. Okay, so a buffer is a solution that resists pH change. So pH is very sensitive. A small amount of a strong acid can have drastic changes to the pH. So that's why you can test it at home. You take a little bit of water and you add 1 or 2 drops of lemon juice, which is a weak acid, but it is on the stronger side of weak acid. So even that small amount of lemon drops or lemon juice that you added, you'll immediately be able to taste that. Part of that is the fact that our senses have developed to detect acids very keenly. The other part of that is the fact that the pH scale is logarithmic. So that means small changes in hydronium concentration has large changes on the pH scale. So a buffer protects against pH changes. So for instance, on the left-hand side, we have a buffer solution. That's the left. and the other one is not buffered, and we just see that this solution has a pH of about 5. Now we add 0.1 molar of hydrochloric acid. Our right-hand side immediately changes color if we add an indicator, and we see the pH drop to 2.3. But the left-hand side that was buffered remains close to a pH of 5. So that means even though we've added the same amount of acid to both of these, the buffered solution resisted that pH change and therefore kept its pH close to its initial pH of 5. The reason buffers are so excessively important, to the point that when I spoke to both the health and veterinary faculties, we tried to work out what the curriculum of this course should be or how we should change it. They effectively told me, you know what, we've got free reign on a lot of things. They not want this and this and this for the subsequent courses, but the one thing we can't skimp on, or that we can't really remove, are buffers. Reason for that, I mentioned it at the beginning of theme 7 as well, is all biological systems happen at specific pHs, whether that's neutral for most of the body or certain areas or even certain organelles within a cell might have very different pH ranges. There's even places where, for instance, close to the cell membrane, we actually have a pH difference. On the outside of the cell, there's I think a basic pH, and the inside of the cell is an acidic pH. So all of this needs to be controlled. It can't get out of hand, because that means certain bodily functions will immediately start dropping, and it can be as sensitive as a change of 0.01 on the log scale can result in severe illness depending on where that happens. So our bodies and the bodies of animals and plants are excessively controlled when it comes to pH. And the only mechanism that bodies have to do this are buffering solutions. So your entire body, every single solution or solvent in your body has a buffer effectively added or controlled inside that to have the pH controlled at the exact specific pH that its enzymes need to work. So a swimming pool is a great example of a buffered solution as well. If swimming pools were not buffered, the moment you have any bit of algae growth or a little bit of a rainstorm, your pH swimming pool will immediately start to change color because certain organisms grow at certain pH much more effectively than other pHs. So in dealing with the swimming pool, they actually buffer it very strongly so that it resists these changes in pH. And then the same applies, for instance, to blood as an extremely controlled buffering solution. Now, a non-buffered solution means any small additions of hydronium or hydroxide gives us large changes in pH. A buffered solution, on the other hand, is small or large changes of hydronium and hydroxide still results in small changes in pH. Before we actually look at how buffers work, I just want to talk about the buffer capacity. We'll circle back to this at the end of this theme. A buffering capacity means how much of this pH change can be resisted. So at some point, depending on how strong the buffer is, we might have if the buffer is very weak, then that means it might resist a pH change of 0.5 log units, and then it effectively breaks down, and then any acid that we add will just have its full effect. Whether if we have a buffer with a very strong capacity, it means it can resist a much larger degree of pH change. Right, so to understand buffers, we need firstly to understand what we call the common ion effect. So given a ionization of a weak acid, so for instance again acetic acid, it interacts with water, it gives us hydronium ions and acetate, the equilibrium lies very far to the left as we've dealt with a number of times. However, what will happen if we have acetic acid and we add to that solution, this is acetic acid if we have an initial concentration of 0.25 molar. The pH will be about 2.67, and then obviously we can calculate from our equilibrium constant the hydronium ion and acetate ions. Now, what will happen if we add the conjugate base to the solution? So we just made a solution by adding the acid to water, and then it equilibrates. We know we've got a little bit of acetate in solution 0.021. But what if we artificially increases this acetate concentration by literally adding something like sodium acetate? So sodium acetate has the same counter ion, the acetate anion. Sodium won't interact with any of the species, so it will remain a spectator ion. But if we now increase this concentration, we'll shift the equilibrium. So if we add acetate, our equilibrium will shift even more to the left, but to do so it will consume hydronium ion, which means the pH of the solution will increase. So this is just another formulation of Le Chatelier's principle, which says if we change the equilibrium, or if we add anything to disturb the equilibrium will shift to counteract that change. So if we increase this concentration, our equilibrium will shift to the left to counteract that change, and in doing so consume some of our hydronium ions. Right, so this is effectively what we utilize for a buffering solution. So, the basic way that a buffer works, again we're looking at acetic acid. So we've added some acetic acid directly as CH3COOH. It's a weak acid. Then we also add to the same solution some of its counter ions. Right, ladies and gentlemen, so you can imagine this at your edge. We add some of the counter ion, in this case as sodium acetate. And we generally do this oftentimes at a 1-to-1 ratio. So we add the same amount of the weak acid and the same amount as its conjugate base. All right, we are anyway at the end of the lecture, so let's call it. We're going to wait too long for the projectors. We'll continue with buffers tomorrow, and then we're almost done with this part of chemistry. Thank you very much. See you tomorrow.